Hello, and welcome back to the channel. Today, we're exploring a critical defense mechanism in building robust and resilient systems: rate limiting and throttling, keeping systems safe under pressure. Rate limiting is not merely an optional feature. It's a fundamental necessity for any public-facing or high-traffic system. Its importance stems from several key aspects. Firstly, it acts as a crucial barrier to prevent system overload from sudden traffic spikes, malicious bots, or intentional abuse. Without it, a surge of requests could easily exhaust your server resources, leading to downtime. Secondly, it directly protects your APIs from misuse or brute force attacks. Imagine a login API. Without rate limiting, an attacker could attempt millions of password guesses in a short period. Thirdly, it ensures fair usage and maintains quality of service, QoS, for all legitimate users. By preventing one user or service from consuming excessive resources, it ensures that everyone else receives a consistent and responsive experience. Lastly, from an operational standpoint, it helps avoid unexpected cloud billing spikes. Uncontrolled access can lead to rapid consumption of compute, bandwidth, or database resources, resulting in unforeseen and significant costs. In essence, rate limiting is a core pillar of any scalable and secure architecture. At its core, rate limiting is a mechanism that restricts the number of requests a client, identified by an IP address, a user ID, an API token, or another unique identifier, can make to a server or API within a specified time window. For example, a common rule might be, allow only 100 requests per minute per authenticated user. This restriction is typically enforced at various layers within your system, most commonly at the API gateway, but also potentially at the load balancer or even deeper within individual backend services. Its primary goal is to provide a safety valve, helping your system absorb unexpected surges gracefully rather than succumbing to them. When a client exceeds the defined limit, subsequent requests are typically blocked or queued, often returning a 429 too many requests HTTP status code, forcing the client to back off and retry later. The effectiveness and behavior of rate limiting depend heavily on the underlying algorithm or strategy used. Here are some of the most common ones. Fixed window counter. This is the simplest strategy. It defines a fixed time window, example, 60 seconds, and counts requests within that window. Once the window starts, the counter begins. If the limit is reached, all subsequent requests in that window are blocked until the window resets. Its simplicity is an advantage, but a drawback is that a burst of requests right at the end of one window and the beginning of the next can effectively double the allowed rate. Sliding window log. This offers much higher accuracy. It doesn't use a fixed counter, but instead logs the timestamp of every request made by a client. When a new request arrives, it sums the requests within the rolling time window, example, the last 60 seconds based on current time. This is more computationally intensive due to storing and processing logs, but it prevents the double-dipping problem of the fixed window. Token bucket. This strategy is designed to be burst-friendly. Imagine a bucket that holds a certain number of tokens. Requests consume tokens. Tokens are refilled into the bucket at a constant rate. If a request arrives and there are no tokens in the bucket, it's rejected. This allows for bursts of traffic up to the bucket's capacity, while still enforcing a long-term average rate. Leaky bucket. This algorithm focuses on smoothing out bursty traffic into a steady flow. Imagine a bucket with a fixed drain rate. Requests are added to the bucket queue. If the bucket is full, new requests are dropped. Requests are processed at the fixed drain rate. This is excellent for ensuring a predictable, steady processing rate for downstream services, but it can introduce latency as requests wait in the queue. The choice among these strategies often involves a trade-off between implementation precision, the system's performance overhead, and how you want to handle bursts of traffic. Implementing effective rate limiting often involves leveraging specialized tools and libraries, many of which are designed for distributed environments. Jinx. As a widely used reverse proxy and web server, Jinx has powerful built-in modules for rate limiting. Directives like limit_REQ can restrict the request rate per client, example, by IP, and limit_con can limit concurrent connections. This makes it a popular choice for edge-level rate limiting. Kong. As we discussed, Kong is an API gateway that offers a very robust and configurable rate limiting plugin. This allows you to apply fine-grained rate limits based on various client attributes, consumer, IP, credential, directly at your API's entry point, centralizing this policy enforcement. Envoy and HA Proxy. These are enterprise-grade proxies that provide highly sophisticated and flexible control over traffic, including advanced rate-limiting capabilities suitable for large-scale microservices architectures. They offer granular control over rules and integration with external rate-limiting services. Redis. While not a rate-limiting tool itself, Redis is frequently used as the backend data store for implementing distributed rate limiting. Its atomic increment operations and fast read/write speeds make it ideal for storing counters and timestamps across multiple application instances, allowing you to implement any of the discussed algorithms in a highly scalable way. Rate limiting often works best when enforced at the API gateway level, providing a centralized point of control and protection before requests reach individual microservices. Rate limiting is pervasive across the internet, protecting a wide array of services and ensuring fair access. GitHub API. A classic example. GitHub explicitly imposes rate limits on its API, typically allowing a maximum of 5,000 requests per hour per authenticated token or client ID. This prevents automated scripts from excessively scraping data or overwhelming their services. Twitter implements a sophisticated system with tiered limits that vary based on the specific API endpoint being accessed and the type of user. Example, verified accounts might have higher limits. This ensures fair access while preventing abuse from automated clients. Login pages. To combat brute force attacks, login pages universally limit the number of failed login attempts from a single IP address or username within a short period. After few failures, the account might be temporarily locked or requests from that IP blocked. E-commerce sites. During major sales events like Black Friday, e-commerce platforms use rate limiting and throttling to avoid checkout overload. This prevents a sudden rush of users from crashing the payment or order processing systems, ensuring a smooth experience for legitimate customers. Multi-tenant applications. In applications where multiple clients share the same infrastructure, rate limiting is crucial to isolate abuse from one client and prevent it from impacting the performance or availability for other, well-behaved clients. This ensures resource fairness across tenants. To summarize our discussion on rate limiting and throttling, rate limiting is an indispensable defense mechanism that protects applications under high load, preventing system overload, abuse, and security vulnerabilities. Throttling, a related concept, adds a layer of fairness and control, ensuring that resources are distributed equitably and avoiding system crashes due to uncontrolled traffic surges. You are now familiar with multiple algorithms and strategies: fixed window, sliding window, token bucket, and leaky bucket, each suited for different traffic patterns and precision requirements. Practical implementations are enabled by powerful tools like Jinx, Kong, and Redis, which integrate well into modern system architectures, especially at the API gateway level. Ultimately, rate limiting is a must-know topic for anyone involved in back-end development, system design interviews, and ensuring the real-world security and stability of web applications. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like, share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.